Okay, let's start our next topic, mathematical modeling. Okay, now you have learned about the signal flow graph, and then we will use um, the signal flow graph in our analysis of the modeling, mathematical modeling. So in these topics, I divided the mathematical modeling into three. The first one is modeling of electrical systems. The second one is modeling of mechanical systems. And the third one is modeling of biomedical systems. Okay, for the first one, we go into the modeling of electrical systems. So the basic components of the electrical system, you can see it in the lecture notes here. We have capacitor, we have resistor, we have inductor. Okay, so this is the, you can see the relationship between the voltage current, voltage charge, impedance, and admittance over here. Okay, so now let's focus on the voltage current, the current voltage, also on the impedance. Okay, let's focus on these three. Okay, so modeling of electrical systems is based on the Kirchhoff law. So we can use either a nodal analysis or mesh analysis, or depending which one is easier to use in each case. So for these topics, okay, for example, let's try to do the first example here, where we have RCL circuit. We have resistor, we have capacitor, and we have inductor. Okay, this is a very basic circuit here. So basically, when you draw it, something like this, the I, so we have the inductor, we have the resistor, and we have the capacitor. Okay, this is a basic RCL circuit over here. So we want to find the transfer function of this circuit. So what is transfer function? Okay. The transfer function is the ratio between the output to the input. So in this case, the output that we want to measure is, we put probe here. Okay, this is our probe, this is our another probe. So we put measure this point, and we want to measure at this point. Okay, this is common. Okay, this is common, and then this is positive probe. Okay, we want to measure the potential at this point, where we name it as E naught. And then this is our input, where our input is EI. Okay, so using the KVL, Kirchhoff voltage law, what is KVL? Can someone let your class know what is KVL? What is the Kirchhoff voltage law? What does Kirchhoff voltage law say? Anyone? Malu or tak tahu? Okay, if you don't know, please go back and Google and find it. Okay, let's use the Kirchhoff voltage law. For the Kirchhoff voltage law, you can see here uh, in every what we call it, in every component, we have the voltage drop. We have the voltage drop on each of the components. So we have a voltage drop at inductor, we have voltage drop at resistor, we have voltage drop at capacitor. So that's the summation of the voltages that passing through L, R, and C is equals to the voltage that supply to the circuit. Okay. Again, the voltages that drops along the components L, R, and C is equals to the voltage that has been supplied to the circuit. Okay. So now we have the first equation. Our first equation, we have here L di over dt, and we have Ri, and we have 1 over C, the integration of I dt. So what is it actually this one? You can refer back to the previous slides. So you can see the voltage current relationship. What we find just now is actually voltage. So V is equals to 1 over C of integration I dt. And then for the resistor, we have Vt Rit. And for the inductor, we have Vt equals to L di over dt. So basically, what we want to find just now is actually voltages. Okay? Voltages. So again, here is actually what we find is actually here is VL, here is VR, here is VC. Okay? Okay, this is the first equation. Okay? And the second equation, we have to find the relationship between the E naught and whatever that close to E naught. In this case, we can find the relationship between E naught to C. So basically, the potential measured across C is E naught. So what we have here is basically VC. We measure VC is actually equals to E naught. Okay, assuming zero initial condition. So when you refer to the Laplace transform videos and the lecture notes, we have the initial conditions. So whenever it is not mentioned in the question, you can assume that the question asks with zero initial condition. Okay, so assuming zero initial condition and transform the equation into Laplace, we can have the equation 1 and equation 2 here provided in equation 3 and equation 4. So in this case, we have L di over dt. When we have L, this is a constant, the value of inductance. So I just leave it as L. And then we have di over dt. So we have the differentiation here, di over dt. So it is the n, we have d, remember, dni over dtn, where n is equals to 1. So what we have here, we have SIS. SIS. Refer back to the Laplace transform. Okay, we have SIS. And then for resistor, we have Ri. So basically, we just transform it into RIS. And then we have the for the capacitor. For the capacitor, we have 1 over C. Leave it as it is, 1 over C. But now we have the integration of I dt. I dt. So when we have integration, we have this term when we transform the integration into the Laplace. So we have 1 over S I S. Okay, so this is EI. We have capital EIS, and then we can do the same for the second equation that transform into fourth equation. So we have 1 over C, 1 over S I S equals to E naught S. Okay, so we can find the transfer function here is GS equals to E naught over EIS, which simply we can rearrange equation 3 and equation 4. And finally, we will get the terms here, 1 over LCS squared plus RCS plus 1. Okay, this is just a simultaneous equation between equation 3 and equation 4. So any questions so far? Okay, hope you understand. All right, next. Now, we expand the problem. Just now we have only one loop. And then what now, the next example, we have the cascaded RLC, RC. This is RC. This is RC circuit. Okay, this is RC circuit here. Now we have 2 loops, I1, and we have loops I2. Okay, again, using the KVL, Kirchhoff voltage law, we can get 3 equations. We can get 3 equations. The first equation, we can come up with this portion. Okay, this portion where we get our equations is contributed by the R1 and C1. Okay? R1 and C1. So what we have here is we have R1, I1, because the current, we define the current in this loop is I1. Okay. So what we have, this is I1, okay, I1. So what we have is we have R1, I1. And then we have C1 over here. C1 is, okay, let me just, what we have here, C1 is shared between the 2 loops. We have in the I1 loops and we have in the I2 loops. So we need to have this term, 1 over C1 integration of I1, because we consider the first loop, I1 as is at the front, I1 minus I2 dt equals to EI. Okay, equals to EI. Like I said before, the potential here is EI. So when the electron travels to R1 and C1, it will have a voltage drop across these two components, R1 and C1. So the summation of the voltage drop across R1 and C1 should equals to EI. Should equals to EI. Okay, now we have equation 3.66 here. Done. Next, let's focus on the second equation. The second equations come from this loop, I2. We have I2 loop over here. And at this loop, we have three components that we have to consider. We have to consider the first one is C1, and then R2 and C2. Okay, so we have here the first one, we have C1. Again, this component C1 is shared across two loops. We have I1 loops and we have I2 loops. Since we consider the second loop now for I2, we put it at the front. We have 1 over C1 I2 minus I1 dt plus we have R2 I2 because it exists on its own here, not sharing with any other loops. So we have R2 I2 plus we have 1 over C2 integration of I2 dt equals to 0. Why equals to 0? Because you can see here in this second loop there is no potential, there is no supply. Okay? There is no supply at all. So the summation of C1, C2 and R2 equals to 0. Okay, now we have equation 3.67. So let's find the last equation. The last equation we must find is related to the output E0 over here. So like the previous example, E0 is actually the voltage of capacitor C2. So what we have here is we have 1 over C2 integration of I2 dt equals to E0. So now we have equation 3.68. Okay, 3.C-68. All right, we have 3 equations. Now we can finish all the jobs to find the transfer function of E0 over EI. So we transform all 3 equations, 366, 367, and 368 here to into Laplace. Okay, we transform into Laplace assuming 0 initial conditions. So now what we have here is we have 1 over C1s, I1s minus I2s plus R1 I1s equals to EIS. And you can do the same with equation 367 and 368, and you can get the equation of Laplace, the Laplace transform of the equation at 370 and 371. Okay, now we have 3 equations here. Next, what we can do is we can use the simultaneous equation and to find the E0 over EI. So basically, this approach becomes quite complex as opposed to the first example where we have only a simple RLC circuit. So we can do a different approach. Instead of using simultaneous equation, what we can do is we can use the signal flow graph. Okay, we can use the signal flow graph to find the transfer function of this equation, of this network. Okay, let's say now we take back the equation, the example, the previous examples. Now we only have a RC circuit without L. We have RC circuit. So I don't want to explain about the nodal analysis. You can read it by yourself. I just want to focus on the solution 2 using KVL and KCL. Okay, using the Kirchhoff voltage law and Kirchhoff current law. So we can write here, we have this equation. Okay, we have this equation. We have E naught. So in this case, I simply transform the equation to Laplace without writing all the equation in the time domain. Okay, I just transform into S domain the Laplace, where we have here the first one. We consider this portion. Okay, we consider this portion. Here, I consider the use of, let's label first. So we have here is actually EI, and then we have E naught. E naught actually we can take the probe, we can measure over here. Okay, we can take the probe. Okay, this is a common, then this is a positive probe. So basically this is the E naught. Okay, now we can see here this is EI. Okay, EI. When the electron travels through the component R, there is a voltage drop, like I mentioned before. When there is a voltage drop, meaning that there is a current passing through. Okay, so we can find the current. Okay, here we can just say that we have the voltage over here is EI and the voltage over here is E naught. Okay, so basically a difference between these 2 points, between these 2 potential EI, E naught, we can use the KCL. So we can say that EI minus E naught over R. So remember V equals to IR. So I is equals to V over R. Okay, so this is potential EI minus E naught over R. So we can get this term number 2. For the term number 1 is basically this portion. Okay, this portion basically the voltage of capacitor itself. So E naught is equal to 1 over SCI. Okay, so from this point we can draw the signal flow graph. The signal flow graph, to draw it, it must be, we have to put the input first, output last. Okay? Input first, output last. This is the input, this is the output. Okay, so now we have E naught, we have EI, and we have I. Okay, so we have 3 terms here. So we have E naught nodes, EI nodes, E naught as a nodes. So the relationship between EI and I is, we have here EI and I. Here is, this is the arrow. So I equals to 1 over R EI. Okay, I equals to 1 over R EI. So I is contributed by EI. So the arrow goes like this. The I is contributed by EI is 1 over R. Okay, 1 over R over here. And then we have a relationship between I and E naught. I and E naught. Again, here we have I is contributed by E naught. I is contributed by E naught. So we have negative 1 over R. So that's why we have negative 1 over R. Okay. And then last one we have from equation 1, E naught equals to 1 over SCI. Is relationship is E naught is contributed by I. So we have 1 over SC. And then we already get our signal flow graph. When we found our signal flow graph, we can find the transfer function using the Mason's rule or Mason gain formula. So remember T1 delta 1 over delta. So in this case, it's very simple. This is the forward path. This is the forward path. So our forward path is 1 over SRC. So this is T1. Okay. So next we have a loop. What is our loop? Loop is basically we have 1 over SRC. Okay? 1 over, this is our loop, negative 1 over SRC. Okay, now we can use the gain formula. So this is delta equals to 1 minus 1 over SRC. And then we have delta 1 equals to 1 minus nothing. So what we have here, we put it into this equation. So finally, you can find that the transfer function of the system is equals to 1 over 1 plus SRC. Okay, so I think I want to stop here. Any question? So please